interaction session you can have. So just let me introduce him before he starts his session. It is my privilege to introduce Mr. Ekant Sharma, an entrepreneur, environmental engineer, and a rising innovator in the global green hydrogen ecosystem. He is currently the CEO, director, and founder of Ekavikalp Private Limited, where he is pioneering circular hydrogen production systems that integrate wastewater treatment with electrolysis, enabling up to 40% cost reduction in green hydrogen generation. He is also the co-founder of HyGoat, a next-generation platform designed for hydrogen guarantee of origin traceability and regulatory compliance across global markets. Mr. Ekansh has previously led groundbreaking hydrogen work at KTH Royal Institute of Technology, Sweden, where he served as a project coordinator for the world's first industrial steel production plant heated entirely by hydrogen at Ovaco's Hofas facility, a pioneering milestone for green steel technologies. His work involved sector coupling strategies, electrolyzer performance validation, hydrogen storage planning, and techno-economic analysis for heavy industry and mobility applications. He has in membrane expertise in membrane technology, semiconductor grade ultra pure water systems, AI driven water energy optimization, PFAS removal, and circular water management, all of which position him at the intersection of clean energy, digitalization, and industrial decarbonization. He has collaborated with major organizations including Volvo Trucks, Hitachi Energy, IMEC Belgium, Horiba, and various European research institutes. A graduate of KTH Sweden in environmental engineering and sustainable infrastructure, he has consistently demonstrated excellence across academic, industrial, and entrepreneurial projects. His portfolio includes contributions to hydrogen system modeling, electrolyzer optimization, and digital platforms for international hydrogen certification. He is deeply committed to advancing UN SDGs 6 and 9 through innovation in the water energy nexus. We are delighted to have him with us today to share his insights on digitalization, AI, and smart systems for the hydrogen value chain, as well as we have one more talk for with Mr. Ekansh. So that will be on policy regulations and frameworks essential for India's green hydrogen mission that is scheduled in coming days. So please join me in warmly welcoming Mr. Ekansh Sharma. Yeah, Mr. Ekansh, you may proceed with your presentation.
Thank you, Dr. Bhargavi, for inviting me.
Yeah.
And I'm really glad to take upon this stage to learn and disseminate some of the experience that I have accumulated over the years. So let's begin. Um, Myself, Ekansh, and we are here to learn and interact about digitalization and AI in hydrogen systems. This is a part of a course for the faculty development program, session 7, AICTE ATAL scheme, scheduled for November 26th, 27th, organized by NIT Raipur. So yes, after the extensive introduction, I don't think there is a doubt about who am I. Well, here is a brief list of my accomplishments and academic and professional collaborations. But let's skip to the main deal. Yeah. So the course curriculum for today's session has been designed in such a way that we learn breadth over depth about the following 5 sections. The opening is where I lay out the challenge briefly in about 10-15 minutes. Why are we talking about AI and digitization for hydrogen systems? Then I'll briefly discuss about the digital technologies. Later on, AI applications, about half an hour. Then how do we implement them and what is the future scenario? Discussing a little bit about the trends. And there we have, lastly, questions, answers, perhaps some integration, and how you peers of NIT Raipur, professors, lecturers, and the whole educational staff can integrate them through your course curriculum, or perhaps get a unique insight about how to actually make and deploy them into the real world by teaching them to students, perhaps. So yes, briefly we'll discuss about understanding the digital transformation imperative in hydrogen, identifying AI ML applications across the hydrogen value chain, certification, automation, compliance technologies, just a little bit, exploring emerging trends and shaping hydrogen future, applying insights to teaching, research, and industrial collaboration, and a little bit discussion about AI ethics, why are they important, and yeah, the course curriculum throughout the session is structured in such a way that we are treading over multiple multidisciplinary topics, so it's breadth over depth. Again, why are we here? Curriculum development, policy certification, hydrogen production technologies, research opportunities, industrial collaboration, AIML applications, or perhaps merely mandatory attendance. Yeah, but the central question or the central dogma still is, why hydrogen? Why are we talking about it? Why is there so much stuff going on around the world, or lack thereof? Well, I think all of us researchers or little bit people with the scientific background do understand that hydrogen is number one element on the periodic scale. It's literally the lightest element and the most abundant. It powers our whole civilization from sun, producing fusion to helium and all the way to iron, and only burns to produce water. But why does it matter today from today's point of view? Because from the idea of decarbonizing the industry, which has taken such a great route after the Paris Agreement in 2015, all the nations have jointly contributed their NDCs that they are going to cut down their carbon emissions. And in this quest to decarbonize, one central point is that we cannot electrify everything. We cannot electrify everything because there are heavy industries such as steel mills, fertilizers, chemical plants that just cannot function on batteries. And humanity does need all these materials to survive and thrive. And therefore, we are talking about hydrogen. But there's also this tension that we are betting big
వస్తున్నా
on
వాయిస్
AI.
వస్తున్నా మీకు
We are betting big on data
క్లాస్
centers,
వస్తుందా
GPUs, and digital solutions.
క్లాస్
They are very exciting and profitable, as we have all seen the rise of ChatGPT in the recent years. But they are also competing with the hydrogen infrastructure. And it's the same problem all over again. Where do we locate the capital? So there is a slight bit of nuanced take on us AI and hydrogen competing over the past years from my personal experiences. Let's say a project is promising $100 billion endowment to scale up a green ammonia or a green hydrogen facility. But past FID, which is final investment decision, a big threshold for deciding whether your project is going to make it or break it, not a lot of capital allocation is happening. Basically, if you're going about 100 billions, only 10% of it is allocated. So there is policy making aspect of it, and there's other aspects. But yeah, I just wanted to briefly mention about it because there is this nuanced take. So this basically shows us where the incentives are lying. I do want to mention it's not a zero-sum game for people who are aware about the game theory. Therefore, a hydrogen native economy means deliberately building the infrastructure for the heavy industry decarbonization. Yes, it's not, it's unsexy. It's not as glamorous as AI, but it is definitely very essential. And the only way we are going to decarbonize the human industrial. Therefore, in a nutshell, I want to summarize why are we talking about hydrogen is because we cannot decarbonize without hydrogen. So, how do we produce hydrogen so far? And I'm pretty sure throughout the previous sessions, you must have heard or have this sort of understanding that there are multiple pathways. The predominant pathway of how we produce hydrogen is via steam methane reforming, here mentioned or showcased via the gray. So there have been color codings. The color codings basically corresponds to how do we produce hydrogen. The predominant way right now is steam methane reformation, which is breaking down the methane molecule to produce carbon dioxide and hydrogen. It's economical, it's mature technically, but also as a result of byproduct, we are getting carbon dioxide, which defeats the purpose of decarbonization. That's why we have all these different pathways. And for the sake of the context, there is solar, there's electrolysis. Electrolysis is green hydrogen, carbon capture and storage is blue, pyrolysis is turquoise, nuclear is pink. So I would call it the hydrogen rainbow. But yeah, it's nice to be aware that there are multiple pathways. And the National Green Hydrogen Mission, under which has been undertaken in 2023 for India, stresses the part of green hydrogen, as in the electrolytic pathway. So yes, let's start about the hydrogen opportunity for India. Well, India in 2023 launched the National Green Hydrogen Mission. It is an investment for about 19,750 crores, roughly about $2.5 billion. The target is to produce 5 million metric tons of green hydrogen by 2030. There has been dedicated renewable addition as well of 125 gigawatts. As a result, there is an opportunity to create about 600,000 jobs. And lastly, but the main objective is to also avoid or decarbonize about 50 million metric tons of carbon dioxide. So this lays out detailed plan of India's hydrogen mission. And I recently, about 2 weeks ago, was in Delhi for International Green Hydrogen Conference, where I met the dignitaries such as Mr. Prahlad Joshi, who is the Union Minister for Renewable and New Energies, and Mr. Abhay Bhakre. And they said this one important thing. Why did we name it the mission? Because it's merely a policy or it's merely a directive that we want to do this by the year 2030, but it is actually imperative that we call it a mission because it's mission critical for India, not only for decarbonization perspectives but also for energy independence perspectives. So I want to lay out this little trivial information for you all that yeah, that's why it's National Green Hydrogen Mission. Yeah, this slide doesn't really fit in, but it is a slight, what do you call, to understand the idea. Why are we going through this and how hydrogen might fit through it? So to explain it to you, on top you have a graph which is roughly called hype cycle. The sources are below. Gartner's hype cycle, which lays down the path wherever a new technology comes in, what are the basic thresholds that it passes through before it becomes mainstream, mature. And you see the technology trigger where technology is just talked about a lot. That's the trigger. Then you have the peak of inflated expectations, followed by a trough of disillusionment, slope of enlightenment, and plateau of productivity. On the bottom hand side, you have the technology adoption life cycle plotted, which is sourced from Rogers' bell curve, as in a normal distribution. Now, we as scientists or researchers might debate whether this is actually applicable for the hydrogen economy, but it is just to lay out the facts and perhaps a bit introspectionally asking each of us, where does the hydrogen economy fit in? We will revisit this because the talk has been centered to AI and digitization, but I do want to ask all of us to question this. Where does the hydrogen economy fit in into these two graphs? So yeah, let's start out. What is the industrial revolution that brings in the hydrogen 4.0? The evolution of industry in the story of humanity has been relentless towards progress, driven not by mere leaps of improvement, but in 1800s we witnessed the industry 1.0. At least that's how I am classifying it. It might not exclusively be industry 1.0, but it started out with steam power. First of all, the thermodynamics stand out. And I do want to mention a little bit of trivial fact here as well. All of you might be knowing Carnot cycle, but Carnot, the guy, was actually a part of Napoleon's inventory, or not inventory perhaps, but he was part of Napoleon's army. And there they witnessed that they could basically marginalize or capitalize on the steam power. At that time, steam engines were merely efficient about 4%. So it's a reflection of how far we have come in these last 200 years or so. But yeah, focusing on Industry 1.0, steam and mechanization were the main things. Before steam power, energy was reliant on wind, water, and muscle, but steam power changed that. And automation and mechanization at scale really shifted. Next up, we have Industry 2.0. I'm specifically not mentioning oil in this, but I'm focusing on electricity and mass production. So 1900s, we have the second industrial revolution. Again, my nomenclature. But this period transformed the production process, making mass production feasible and amplifying the speed at which goods could be manufactured and delivered. In 1970s, with the advent of computers and automation, we have the Industry 3.0. And this is where the foundational stepping stones of internet were also laid down. A lot of you might be aware of ARPANET, which started out as a research project for industry or defense back in US, which laid down and culminated as World Wide Web in 1990s. So it is all about networking and little digits or little computers talking to each other in Industry 3.0. And lastly, we have the Industry 4.0. Again, my terminology, which stems from cyber physical systems, AI, IoT, blockchain. But to summarize this in a brief 7 layer, we have, sorry, summarize this in a brief 7 layers. We have the physical layer, applying this to the hydrogen economy. It stems for all the physical setup that you can see in the facility, electrolyzers, storage tanks, transportation, everything. Then you have the sensors attached to it, be it Internet of Things sensors, smart meters, whatever that can be recorded and transmit into a digital information packet, which is being transported into the communication layer. You can have the edge devices here, 5G, whatnot. Then it goes all the way to the data layer, where we have large scale time series databases, data lakes, a whole repository. This further translates to the intelligence layer, where you have small or large AI ML models, perhaps some digital twins as well. Again, this lays down to application layer, where you can do the optimization or model predictive control and all sort of calculations on top of it to make sure that the physical layer is working nicely. And lastly, you have the trust layer, such as blockchain and certification.
Because
So I do want to see that over the course of the last 200 years, from 1800s with the
so,
advent of Industry
हाँ
1.0 to
हाँ
Industry
जी आ
4.0,
जाओ
what actually changed? There has been changes
मिला मिला कर ले पहले
from manual to autonomous.
मजा आ
I'm sorry,
गया
I would advise the participants to please mute yourselves. It's not helping
Dingle,
me to concentrate.
cathedral, dingle.
So what really changed over the last 200 years? Well, the manual things are becoming more autonomous. The reactive things are becoming more predictive. Siloed approaches are becoming more integrated, and opaque things are becoming more transparent. These are the four main inferences that we can actually calculate over the last 200 years. Perhaps this trend would continue, we don't know, but we can rely upon these four inferences and build upon it. That how do we build upon it is the most important thing. So let's continue. Hydrogen value chain research and work avenues. I think this is something that would really affect or like actually be good for people who are participating in this session. And what are we seeing these icons? These icons might invoke some different things in your mind, but these are basically the five stages of the hydrogen value chain, all the way from production to things such as storage, transportation, and final analysis. But why do I mention these right now? Is these are some things that could be really inculcated in your workflow directly. So for production, we have the ML optimization, the predictive maintenance, and energy forecasting. For conditioning, we have the purity monitoring, the process controls, and the quality assurance. Fun fact from my personal own experiences of the Oaco Force project, the gas sensors measuring the purity of hydrogen and oxygen respectively were the thing that were most susceptible to breaking down. So my own interaction with the technicians back in Hofors, they mentioned that these are the things that is more susceptible. Storage is ridiculously expensive as of now, even with the advent of type 4 cylinders, which we were talking about in the few other earlier sessions. But there is something that we can do in this regard. Is it the capacity optimization? Is it the real-time flow analysis of optimizing the times to store, when not to store in the storage tanks, and to identify leak detection as well if you have much more leeway in sensing. For transportation, we still are figuring out things, but LOHCs are a nice way. But there is route optimization with a central AI. We can also manage the fleets, and we can also do the demand forecasting, which is really important to sort out the chicken or the egg problem for development of the hydrogen value chain. And lastly, we have the end use where we can do the usage analytics, carbon accounting, and certification, which I'm particularly biased to. So, in essence, through this slide, I've laid down the five specific pathways where you, as researchers, as professors, or people who might be interested in employing hydrogen into your workflow, these are some things that you can directly work upon integrating with industry. Now, on the project side of things, there are four stakeholders which I am trying to address via my ventures. Why do I mention this? This might not be directly relevant to you, but I think it's a good way to keep in things in our brain. And who are these four stakeholders? They are producers. By producers, I mean uh, people who are actually deploying the projects. and producing hydrogen or their respective derivatives. There are regulators who are laying down the policy making schemes. In this regard, we have the MNRE, who laid out the National Green Hydrogen Mission. So they provide compliance, they need compliance oversight, the data integrity. There is a pain for manual verification and a fraud risk if somebody is providing incentives to the producers to development of the hydrogen value chain. They would require that they are actually producing this green hydrogen. Henceforth, a real or low hanging fruit would be to provide a real time dashboard that, yeah, this is really, really happening. Then we have the producers where they do really, really need the certifications and the low cost attached to it. So, natural solution again is an automated measuring, recording, and verification software. Perhaps off-takers who are really the consumers in this side. This is a fancy word of saying yeah, consumers, but they are really people who are utilizing the green products such as hydrogen, ammonia, methanol, or whatnot. But they are the people who really want to know the authenticity of the green molecule for what they're paying this premium for, at least in the immediate 2 to 3 years, until we achieve the cost parity with gray hydrogen. What do they require? They require the trust that whatever they're buying is actually green or not. And this green might be differing from one country, one framework to another. And lastly, we have the auditors who do require that there is uniformity in their workflow and there is no data silos. There is a data silo that they might need to actually check on to get on the whole picture of where the data is flowing and if it's being tampered with or not. And their need is efficient verification workflows. I'm a bit biased in this slide because this is directly the thing that I'm trying to address via my venture, High Growth, Hydrogen Guarantee of Origin, Accountability and Transparency Platform. But I did want to mention it because it's important to keep it in our head. What is really we are targeting when this industry is really taking off. And again, a segue of how things are and how things could be. And I'm trying to show this via the next two slides that are about to come. So first of all, we have the producers who are collecting the data. And this data, after being collected, is being documented by hiring a lot of expensive consultants. We're making reports and supporting documents. Then this data is being verified by the auditors who are visiting the site visits. They're reviewing the documents itself and also interviewing stakeholders. And lastly, we have the approval where the certificate is actually generated that this molecule that is being audited is actually green and not. And then this certificate gets transported to the producer, and then they can claim the carbon credits or actually sell their respective output for the aforementioned price as green molecule. But in a nutshell, this is what the certification is this is how the certification is happening as of now. All these figures might not reflect the actual price, but they do give you some sort of indication on how things are as of now. But let's paint a picture of how things could be in future when this certification challenge is digitized. So the certification challenge in digital format looks like the following. We have the data collection, which is continuous because we have IoT sensors on board. As I was mentioning in the previous presentation, previous few slides above the physical layer, we have the sensor layer. So this is the sensor layer that I'm talking about. IoT sensors providing automated logging, cloud storage. Documentation is also automated by providing specific workflows for specific industries. We have AI generated reports, not necessarily, but we do have a definite workflow with pre-filled templates providing digital signatures. Then we have the verification. Now, this could be actually physical or remote, depending on how sensitive we are going. But we do have pre-validated algorithms which can get this job done in much more less time than is actually done in the manual way, and also a review. And the whole process could actually be shortened by providing a blockchain certificate, the QR code, which could be analyzed by the off-taker directly, and the whole process is just reducing the time taken from end to end, from data collection to approval, from perhaps months to even days. What is the impact of this manual versus digital? For the ambitious target of 5 million metric tons, which is laid out by NGHM, National Green Hydrogen Mission, we have, or we would be having millions of batches. But without digitization, it would be really, really impossible to get them all certified or validated. And this is sort of the problem or the solution. It's also important to look at the economic situation of hydrogen. Now, in a nutshell, capex is capital expenditure per megawatt of an electrolyzer and all of its surrounding components. So for instance, let's say we have an electrolyzer, alkaline electrolytic system, which costs about 4 to 6 crores. The surrounding balance of plants and utilities would cost about 1.5 crores. Storage compression, about 1 to 1.5. Civil and electrical systems, about 1 crores. And safety and monitoring, about half crores. So in essence, the total cost for 1 megawatt of electrolyzer system with all the ancillary services, balance of plants, and stuff would amount to about 10 crores per megawatt. Keep this figure in the back of your mind. It's not a rule of thumb, but it does give you an indication of the amount of capital that goes into 1 megawatt of electrolyzer system. Now, these would differ if we just nudge the electrolysis from alkaline to proton exchange membrane, but it's a good figure to keep in the back of your mind. But how does OPEX count? And here it's analyzed. So for 1 year, electricity cost is about 60 to 80%. In Europe, it was much more higher because, I mean, this is again from my experience. In India, we might be having a bit more cheaper electricity, as with the omnipresence of solar and wind, which does really, really good play into our hand. But there is water treatment, which is about 8 to 10 kilograms per hydrogen produced. This is about 10% of the whole OPEX. O&Ms is about 2 to 4% of the OPEX. Stack replacement is about 15 kilograms per H2, which is in the timeline about 10 to 15 years since the installation of the plant. And the compliance is about 10 to 50 lakhs per year, perhaps a bit more, but depending on the usage. And renewable electricity at 3 rupees per kilowatt hour is about 180 to 220 per kilogram of hydrogen produced. So what is the LCOH? And by LCOH, I mean levelized cost of hydrogen. As of currently, India did won the latest tender secured by SECI, and we did actually record the lowest price. Although it for domestic offtakes, we did have the price which was won by Acme at 49.75 per kilogram of green ammonia. And the current reality is that we're producing about 350 to 380 or around 400 kilograms, 400 rupees per kilogram of green hydrogen. But NGHM sets out a very ambitious target again, because we need to achieve this cost parity to gray hydrogen to really, really make sure that hydrogen economy is taking off. And they set it out to be 100 rupees per kilogram. It's nice to look at the capex and the opex. Capex is definitely heavy in the green hydrogen or P2X projects. But OPEX is really where you're making or breaking the case. And electricity cost is about 60 to 70% of it. Another important thing to look at is the water treatment and the land and the other essential aspects of what makes or breaks a project, the geolocation of it, how um, much closer it is to the port or not. So all those things are really important before a P2X project actually is laid down and commissioned and is operational. But the key lever is, which is working in our case, we have a absolutely low renewable energy electricity costs, around 2 to 3. The electrolyzer domestic throughput is not there yet, but we would be there in some time. There have been incentives, uh, and as I said previously, looking at capex and opex, it's nice to keep in our heads that electrolyzer or the capex is not the most important thing to look at. We can actually import a bit of it, but we do really need to manufacture in order for India to be sustainable in the long-term aspects of achieving energy independence. But the key lever is that LCH of 100 rupees per kilogram is achievable. And the assumptions that I made to do this calculation is that the specific energy consumption of the electrolyzer is about 50 kilowatt hours per kilogram, working and operating about 8,000 hours per year, which is also not 365 days. So not the running full time 24/7, 365, which is the AL baseline. Water consumption is about 9 to 10 liters per kilogram of hydrogen, and the sources are various industries and the National Green Hydrogen Mission themselves. Okay, market projections. The digital edge to boom. By this slide, I meant to show what is the market segment for all these digitization technologies. The key metric here mostly is about compounded annual growth rate, mentioned as CAGR, value and timeline on how it's is right now and how it is going to be in the few years to come, and their respective references. So I want all the participants to please glance through this table to understand this is really happening, and how to make or take advantage of it. In a nutshell, the key numbers are that we are having a total investment of about 8 lakh crores. We are having a digital allocation of about 1.2 lakh crores. The job creation, which was previously referenced as well, is about 600,000, perhaps even more. And market compounded annually growth rate is 20.89% for the India hydrogen market. Now, what are the opportunity zones? Understanding the stable in a nutshell. There we have the platform development. So a lot of software, a lot of reg tech and measuring, recording, and verification systems. Then we have the AI solution stack, which is optimization, predictive maintenance, fault detection, replacement, all this kind of stuff. How can we integrate at the source or the data collection layer? We have integration for sensor networks, edge computing. How do we do consulting in this regard? So rather than vanilla consulting, and by vanilla I mean like manual consulting, project to project base, we can perhaps allocate ourselves to a digital transformation service, which where we can scale to a lot of people and much more amplified way of scaling. And we should also train ourselves in digitization in the AI systems by having dedicated skill development programs. So yeah, that's in essential what I wanted to convey via this slide was the digital hydrogen boom is happening, and these are the market segments, and these are the figures and opportunity zones respectively. But Again, a very specific slide for what it holds for perhaps NIT folks back in Raipur. There is skill gap, as in the industry does need a lot of data engineers, a lot of machine learning engineers, a lot of IoT architects, blockchain developers, digital compliance specialists. And the current supply is that we do not really have the H2 specific programs. Perhaps this is something that we can work upon. We do have silo disciplines, as in the people back at the chemical engineering department. It might not be, I'm not particularly targeting this Baxter university, but we should be talking to each other and working together in a collaborative manner. And rather than focusing on the theory, we should also work with industry a bit more. So perhaps it would be better to reach out to the folks or your friends back in the industry and sort out an interdisciplinary curriculum. The research frontiers: AI for electrolyzer optimization, digital twin development, federated learning models, blockchain certification, predictive maintenance. The constraints again are that we have very limited data sets. The data sets might be IP protected, might be proprietary. We don't really have an access to a real plant. The industry is not really collaborating with the academia. We don't really have a lot of industrial PhDs going on. The data or the research that we are doing is not really translated into the real economical wonders where industry is actually absorbing this research. So we have those. And to really question again, what does really industry want and what does really academicians want? And if it is to sort of bridge these two things together. So industry does really want ready to deploy solutions, which can actually reduce their time to do end-to-end things and to reduce money. That's what, in essence, they care about. They do really want validated models. They want trained workforce, and they want joint R&D. And there is this current gap. So with this in mind, the triple challenge for academia is really the skills gap, the research frontiers, and the industry connect. But let's imagine running back or running forward 5 years. So imagine each of us role in 2030. What if the chemical department in NIT Raipur has a hydrogen data science for MTech program? They could be actually having a digital hydrogen lab too, right? Publishing leading research on AI for electrolyzers, perhaps. Also, we do want good for our students or whomsoever we are teaching. So we naturally want them to be placed in 15 to 30 lakh per annum package. Now, this might be very specific, but do you all understand where I'm coming from, right? I collaborated with International Energy Agency, IRENA, for standards development, perhaps, and authored textbooks. So basically, development for skills, development for students, development for competency. And on the right-hand side, you have some of the established things that we can do for our students as well. But yeah, just keep in mind, like, from where we are right now in 2025, what could happen in 2030? And this was the part one, the digital stack. I think I'm running low on time, so I might need to fasten up my pace because this is now really informational dense. But the digital technology stack is how we are going to build the hydrogen infrastructure from a digital point of view. I have this excellent infographic where we are laying out the whole 7 layers and what does it encompass in each particular layer. I'm going to start from the layer below. We have the layer 1, physical layer, which basically encompasses all the physical things that you might see in the industrial facility. It encompasses all the electrolyzers, the compressors, the rectifiers, the storage tanks, the balance of plant system. Everything that you see in the industrial facility is the physical layer. On the top, you have the sensors, temperature, pressure, flow rate, purity, whatever, power, whatever, all the sensors. A rule of thumb is there is definitely at least 100 plus sensors per megawatt capacity. Third layer is the communication layer. MQTT broker, again, a way of how things are being communicated from the sensors to actually the computers or the local edge devices. You have Modbus, you have OPC, you have Industrial Ethernet, 5G LTE. On the edge computing, we have an edge computing by edge computing. What is edge computing actually? Edge computing is basically a small computer which is located having not that much of compute or computational power. So basically a small server or small computer which you might use. The analogy here is that you use a PC rather than a server. So edge computer is a PC in this regard, and server might be the big computer where most of your computations are happening. On the cloud, you have the data lake, the analytics engine, the REST APIs, and the backups or the data repository. On the intelligence side, you might have the AI models, the digital twins, and the anomaly detection stuff, which is ingrained into the AI models. And on the application side, you have the operator dashboards, the blockchain modules, the external APIs, or the alert system. Sorry. Okay, rushing through things. 10 megawatt hydrogen plant digitization comprises of about 500 to 800 units of sensors. Going through the previous slide, I said at least 1 megawatt of a hydrogen plant comprises of at least 100 sensors. But multiplying this to 10 megawatt or scaling it up, this is the basic industrial input in terms of sensors, in terms of data points, in terms of data volume, in terms of network bandwidth, in terms of processing latency, and the cloud storage. Fun fact, during my time researching at the Waco first 20 megawatt, I approached the engineer to ask for the data. They told me they have over 70,000 data points at a millisecond frequency. So they did really ask me, how much frequency do you require? How much data points do you require? Question again here becomes, too much data can be a problem. And my task in that time is to identify all the sensors that I need to understand and research on in order to provide a good inference on what is really happening in the electrolyzer and how can I connect it to the task at hand. Briefly rushing through the communication protocols, you have the three major protocols. MQTT, the full name stands for Message Queuing Telemetry Transport. OPC UA, Open Platform Communications Unified Architecture, and Modbus, Modicon Bus protocols. Most of them are used as industrial grade communication, not algorithm, but communication protocol of how things are being transferred from the physical layer to the sensor layer. Modbus is the oldest one. It is what programmable logic controls are used. It is also the most mature one, but bandwidth is a bit low. You have OPC, which is offering a bit more bandwidth, but there is much more latency in that. Again, there is a nuance in you can either go bandwidth or you can either go latency. And there's also a uh, there's also a metric to choose from a security perspective, and MQTT is the most secure from this perspective. But yeah, in a nutshell, these are the three main protocols for the IoT, or how the data is transferred from the physical layer to the sensor layer. Digital twins. Well, a simple question might be, what is a digital twin? We have twins who are born at the same time in the real world, but digital twin is basically a mimicry of what is happening in the facility, and you have it on the screen where the physical layer is being represented digitally. So therefore the name comes, a real-time virtual replica of a physical hydrogen system in this case, that is being displayed on your dashboard or the screen is the digital twin. What does it do? It predicts the future behavior. It predicts or enables us to have the what if simulations, and it also trains the operators without actually dabbling in the physical risk. standing nearby an electrolyzer, perhaps. There is the three levels of the digital twins. Starting from the level one at the bottom, we have the equipment, herein the PEM stack. The models and the capabilities are as follows: thermodynamics, electrochemistry, degradation, and current and voltage curves, VI curves. Then you have the level two, which consists of the whole of the production facility, which monitors the process flows, energy balances, control systems, and the water integration. And then you have the fleet twin, which might be encompassing or having scope of multiple facilities over time. So, for instance, uh, now I'm just mentioning this. I'm giving you an analogy. All of the Tata facilities operating the green steel plants in India might be operating on the fleet twin level three, but the respective facility in Mumbai as to Jamshedpur might be working on the system twins. Okay. Going forward to the digital twin architecture, how the data flows from end to end. So you have the physical layer, the data flows into the data layer where you influx the database from a time series or time scale database. There in the middle, you have the digital twin, which is the virtual model of the physical layer. It incorporates the physics-based physics module, perhaps an even machine learning hybrid, which detects and simulates what is happening on the physical layer and does the simulation, sends it to the control layer where all the data is being analyzed and controlled. Now, this could be intrinsic or extrinsic. Good research here that I was personally doing was I was doing model predictive control in the intrinsic side where I control the layers of the physical assets, and I was optimizing them via reinforcement learning on the extrinsic layer. Here, model predictive control controls the sensitive part of it, and reinforcement learning, although compute heavy, but does provide avenues for optimization on the extrinsic part of it. And the legend is as follows. But this does give you an insight on how the digital twin might be operated in the facility and how the data flows from the physical layer to the control layer. And the data flows back from the control systems to the physical assets via PLCs and the closed loop. A good thing to look at or keep in mind is that the digital twin might not be connected to the internet, as in it's a black box, and it's a good way that it is kept as a black box because we don't want a cyber attack coming in. Yeah, my bias again, blockchain for hydrogen certification, but to not keep it complex, I would define blockchain here. So what is a blockchain? Blockchain is type of a distributed ledger technology that records transactions securely across multiple computers. How does it do that? It stores information in blocks that are digitally linked together to create an immutable chain, hence the name blockchain. The picture on the right hand side does give you an idea on what blockchain might be, not literally, but in a digital sense. This is what a blockchain is. That means it offers the following things. It offers the immutability of the data. It cannot be changed. The data cannot be changed once recorded. It also offers decentralization aspect and the transparency of it. Now, a real world example of blockchain is, we all know, Bitcoin. Uh, an unnamed guy back in 2008 wrote a paper where he posted what is a blockchain and the rewards of it we are seeing right now. As in the blockchain, Bitcoin a few months ago crossed one Bitcoin was $100,000. But what unique insight he did was he gave this peer-to-peer information systems which offers decentralized access, therefore not for banks, not for It's a digital asset which anybody can use. And his innovation was the decentralization blockchain for peer-to-peer digital cash, introducing a consistent mechanism. And how it does that, it offers the proof of work by doing the work of hashing the block, not make it complex. In essence, blockchain is literally connection of blocks linked together. What it does, it offers immutability, it offers decentralization, it offers transparency and automation. A technical architecture of blockchain might look like this. I'm a bit biased again because this workflow is inspired from Higot and how it is going to work. We start off again with the sensor layer, which processes the data, provides it to the Oracle. Oracle here sees through all of it, does a robustification algorithm or validation of the data, does the format conversion, particularly from the sensors to what is taken by the particular platform. Then there is a smart contract attached, which verifies and checks the logic. In this case, 2.0 kilograms CO2 equivalent per kilograms of hydrogen, which is the standard for India's green hydrogen certification scheme. This metrics or threshold is what singularly represents what is green hydrogen in India. So that's why it's placed there. Then it generates a certificate. Once certificate is generated, it is stored into the blockchain where it could be easily accessible by the consumers or the off-takers. And then the query is passed on to verification API and the QR code is generated. So how does this provide access to the various stakeholders? This whole method can provide access to the auditor, to the regulator, and to the buyer. Buyer here is an off-taker or the consumer again. But why blockchain again? So immutability, transparency, decentralization, and automation. This is the only things or the four major concepts of what blockchain offers here. Yeah, I did mention 2 slides ago. Why should we keep the digital twin or the things in a black box? And this is here because wherever you're having digital stuff, there is an option that hydrogen plus digital is a new attack surface. And this is mission critical because imagine like if you have a 10 megawatt plant and somebody could just sabotage it with via one single digital command. So that is definitely not acceptable, right? So hydrogen plus digital is a new attack surface, and how can we bestly safeguard against it? Well, we can have a simple black box that we just don't connect to the internet. First things first. But there is also social engineering and other aspects of it. So in a nutshell, there's two types of threats. One is that there is a hydrogen specific risk. You have a safety systems compromise, production data theft, certificate fraud, and supply chain attacks. Or you have the industrial control system attacks, which are targeted, ransomware, malware, or insider threats. So how do we defend them? We can defend them in a multiple ways. There is a dedicated framework for that, which offers 3 or 4 layers of protection. But let's not get into that. The important thing that I would say for us to ingest from this slide is how do we navigate the cybersecurity layers? We should be employing the best practices, such as we should be looking security as a first design principle. We should do a threat modeling, which is a form of stride is a form of threat modeling. Secure development life cycle in the design phase. In the deployment phase, we have the penetration testing, wherein you hire a third person to actually crack the code or specifically target your systems to see if they're vulnerable or not, and if the person can get in through. You do a vulnerability assessment, VAPT, vulnerability assessment and penetration testing. You also do security configuration, and you harden or access control or provide the tiered access to people on the basis of their work. In the operations phase, you have 24/7 state of control monitoring. You have incident response plan by creating it thoroughly. You provide or undergo regulatory security audits, and there are compliance frameworks that you can refer to while designing all these standards. There is also AI-powered security that we can go through. But in nutshell, this is too information dense, and I don't mean to keep it that way. We have two ways of going on with the hydrogen and digital threats, hydrogen specific and industrial control system attacks. And these are the best practices that we should be taking in mind while in order to counter or prevent or mitigate cybersecurity attacks. But the basic thing that you can do too is if you are unsure, just don't connect to the internet. Rushing through part 3, AI and machine learning in hydrogen. How does AI transform hydrogen from produce to certify? Basically, in a nutshell, to produce with continuous assurance. We are revisiting hype cycle again. As an introspective slide, I want to posit this question to all of us. Are we in an AI bubble? 2023, November, we had ChatGPT 3.5, which was a voila moment that, yeah, this thing is actually working. And I think in December, all of you might be worried. How do we detect AI in our students' essay? How do we detect AI in our students' homework? And I think it's important to notice the stage of development over the last 2 years that we've had. A lot of us might be thinking that, yeah, AI is not really, really good, and it just is so bad sometimes. Personal annotation that I want to refer to. I have encountered a bug in my code. I want my AI model to fix it. I tell it specifically, this is the problem that I'm having. While countering that bug, it does fix that, but it does introduce another bug into it. So I don't think that it is really, really that good, the automation that it's providing. And with all these big companies investing in themselves, I posit that probably we are in an AI bubble. But the question here remains that probably we are past the technological trigger. We are somewhere between peak of inflated expectation to a trough of disillusionment. But what is going to happen soon? And as a researcher at NIT, I think it's important for us to understand that we are experiencing exponential progress, which is hard for normal humans to understand. So I posit again, are we in an AI bubble? And I think it is for you to answer that question. But let's move ahead. So the AI opportunity in hydrogen. What what can we do by deploying AI into hydrogen systems, and what are the basic avenues? We discussed this briefly initially, but now we're going to dive in a bit deep or depth-wise. So before AI, we have reactive operations, we have manual optimization, we have scheduled maintenance, we have post hoc analysis, and we have siloed insights. What does AI do? Not the generative AI, the chat GPT here, but the predictive AI. We have the predictive operations, which helps and prevent issues. We have the optimization in real time, as in continuous. We have the condition-based maintenance, which only intervenes when it is required. And we have real-time analytics. So the following 5 pathways are here. production-based optimization, predictive maintenance, quality controls using support vector machines and autoencoders, automated certification for GHCI or EU markets, energy forecasting. And now next slide discusses the AI maturity levels. Yeah, so this I've compiled and I would give you about a minute to glance through it, various avenues where we can focus on, and what are the expected outcomes for it. This is heavily researched from the four publications that I've mentioned as source below the table. But yeah, you can basically simulate and ensure the electrolyzer is working efficiently and even improve it by deploying neural networks such as convolutional neural networks and artificial neural networks. And the expected outcome could be that you have a 5 to 24% reduction. It is mature. The problem here again becomes that we have developed this model, uh, but you don't want to test it on a scale of 1 to 5 megawatts. So there is always this deployment problems. But I think it's good to delve in all these hydrogen domain applications for electrolyzer efficiency, predictive maintenance, energy forecasting, quality controls, process optimization, fault diagnosis, demand forecasting, catalyst discovery, safety monitoring. Again, AI is a very mathematical dense field. So even if you don't might be knowing the computer code or the respective syntax for it, if you have a good mathematical background, then you can understand AI. It is not the easiest field to get into, but with information at your key press, again with the AI models, we can learn and deploy and perhaps practice all these different domains. I am going to run through this slide with a brief code snippet on how the problem one, electrolyzer optimization, could be handled. So in electrolyzer, efficiency varies with temperature, pressure, current density, the electrolyte concentration, how to use the electrolyte, is it NaOH, KOH, and all these manual approaches on how we target these are. We have a fixed set points with a one valve, with one button here and there. We do the periodic adjustments at an frequency of, let's say, 1 working day or 3 working days, or a weekly or monthly fix, and we are experiencing suboptimal performance. Now, with digital twins and AI-based optimization, how would we go on about it? We are going to get or run a simplified ML optimization where we import this library, sklearn ensemble. We import the random forest regression model, which is a automatic regression module. We import NumPy library. We train the following two-dimensional sets for temperature, pressure, current concentration R. On the y-axis, we train operational data efficiency. And the model is trained for about 100 estimators. And then we predict and return the results by following this code of a simple F loop. Optimization 2, neural networks for electrolyzer control. Here you have the following 6 features. Again, we want to optimize for. This is what it looks for when we are doing the hidden layers. This is not really displayed in the diagram or the code perhaps, but it's important to understand, to visualize how the neural networks are working. And this is what we are outputting. So basically, we're inputting some of the metrics that we really care about to optimize the electrolyzer. And what we are getting as an output is the recommended or the optimized production rate, efficiency, and stack health. How do we go on about it in the forms of data flow? We take in the raw sensor data, we normalize and scale it. We do the neural net inferencing here, which is rectified linear activation function optimization. And then we do the prediction and the control signals. How do we apply this to the industrial focus? We can apply it to all the despective electrolyzers, the PEM, the alkaline, the anion. For SOEC, it's a bit more thermal management involved because we are operating not with the liquid water, we are operating with the steam. But the training progress is compute heavy. So it's again important to know and devote our compute resources efficiently. How do we measure these? We have the average error, the root mean square error, and we test them. What are the benefits about it? That we can actually get real-time production rate optimization for it. And we can infer, we can have a low latency. We can have a direct cost reduction potential. So this, in a nutshell, is how a neural network for electrolyzer control could be applied from a research perspective. A real deployed examples are as follows. We have an operational plant in EMEC on-K, which offers real-time AI control of hydrogen plant. More cost-effective production is actually demonstrated here. Siemens is actively also involved in digital process twins. They have a commercial product going on where they offer G-proms based modeling across accelerator. ABB is also having their sizing tool, which offers 18% LCH reduction. Air Liquid Allison platform offers 3.5 billion data points from 500 plus plants. And Linde AI implementation has 300 plus use cases where they are accounting for 32% of 4,000 plus efficiency projects tied to AI and digital. So it's not merely theoretical, it is actually being implemented in larger scale. But from an Indian perspective, I think it's important for us to understand that we need to understand how these various venues could be applied to. And perhaps later, when we are mature enough with deployment and compute, we can scale it up. Another application is materials discovery and catalyst optimization. I think Dr. Bhargavi would be knowing much more about it than me. But the traditional problem, again, is if we have a literature review, we formalize a hypothesis, we synthesize a sample or a day or two, then we test it, analyze results, and repeat years. This is the manual part of it. How do we do it with the AI process? We employ an ML model. We screen millions of combinations. We reduce the experimental trials, not by 90%. I mean, this could be a placeholder number, but the time it reduces is from years to months. How it works, another code snippet. We generate different candidate spaces. The candidate could be different metal oxides. Metal ratios are given here as follows. The result could be various thousand combinations. We import sklearn ensemble gradient boosting regressor from the sklearn ensemble library in Python. Then we train on the different data, predict the different candidates of what could be the actual metal oxide samples that we should be working on. They deploy an active learning loop when we select definitely the biggest candidates. And then we retrain with the model data. An example here that I quote is from this particular publication. This is University of Toronto. They had a research question on PEM electrolyzers need better OER catalysts. Current is its iridium, or the catalysts in the PEM are really, really expensive. So how can we find something which is a bit less in the cost terms? Their AI approach involved to database about 6,000 different spinel oxides. Their workflow was to employ a random forest and the FT validation. They discovered a novel material which is cobalt 2.5, gallium 0.5, and oxygen 4. And this is how they're working. The graph that you're seeing on the right-hand side shows the overpotential at the particular current per centimeter square and the Tafel slope. But my point of view of mentioning this particular study here is that this is actually being implemented and there is good work to be done. Now I want to run through on for people who are not aware for ML model, who don't know how to get on about it, is to start by experimenting and working. We have access to various coding models now, which can guide you through it. Start with a very simple model or experiment, lay down your research question, and start experimenting with open source tools, which even provide GPUs. There might be different stuff around, there might be different prerequisites, but yeah, use a simple random forest model, use a simple XGBoost model, and use the following open source tools to get on with it. Later on, you can advance to a bit more higher models. Once you have gathered a thorough understanding, then you can even deploy reinforcement learning. But there is ample amount of stuff that can be helped and learned in order to undergo ML competence development. Here is a slide which mentions the basic data requirements for different models. On classic ML, which is vanilla, you need at least 1,000 to 5,000 samples. Again, the important thing that I want to mention here is AI models are as good as the data you feed them until unless you're using RL, where reinforcement learning creates its own data. But the nuance there is that you need more compute. RL is the most compute heavy thing algorithm from machine learning perspectives, but you need about 10,000, 5,000, 1,000 to 5,000 samples. Recommended is the higher amount of samples. Again, the data quality is important. We are all aware of this known adage, trash in, trash out. This applies to ML models too. Once you have gotten acquainted with the basic models, RF, random forest, XGBoost, then you can progress to time series, where you need a time series database. At least a good recommendation is to have 2 to 3 years of good data. And then you can advance to deep learning nets, where you need at least 10,000 to 5,000 samples. This is not a rule of thumb. Again, it depends on project specific. For starting with a simple model on classic ML, I think it's good to start with small, see of how you are getting the desired result in terms of the autoregression. Are you getting the desired root mean square error? Is it up or really applicable for your workflow? And then advance in a tiered manner. The data quality checklist again is, for hydrogen, always pair ML predictions with explanations. Trust in this case is transparency and track record. Building your first AI model, I run it through with bunch of code snippets. You import a bunch of libraries. You pour in the data. You store it in a data frame. Pour in all the different factors or parameters that you really, really care about on the left-hand side. You simulate efficiency by providing a roughly equation on how these parameters are interacting with each other. And then you clip to a realistic range. This is all about data analysis. Step 2 is you do the exploratory analysis, where you again start off with importing libraries, deploying a correlation matrix of all these particular parameters that you've just selected, and displaying them. Then you do the training of the model. These are again libraries in Python. Split the data, train the model on a random forest auto regression, fit the models across different domains, different dimensions, and actually deploy it by importing, again, a lot of libraries, defining the data, what is the actual format that you want it out of, and the features that you want, and what does the model really, really want to predict. So the 4 steps are data collection, exploratory analysis, model training, and deployment. Industrial collaborations, how to partner. Well, I wanted to say I don't know much about this, but perhaps whatever limited experience that I've gathered through my time, I can say a little bit. There are 4 ways of engagement, what I'm proposing: sponsored research, joint development, consultancy, or incubation support. For sponsored research, we can have the company or the industry defines a problem, university executes the research. Results could be shared after a publication delay. This is what we experienced in my case back in KDH and Owako Green Steel plant. We did not publish the results for the paper, and the previous paper was simulating a bunch of stuff, but it was regardless a good experience for the industry and for the research institution. A joint development in this case could actually be really, really good if we can get on about it. But yeah, IP protection and the proprietary data is really the bottleneck here. There is also consultancy for quite a lot of research and academic stuff, which could be short term or long term. There could be a company spin out of it. And there is incubation support for the really boosting the next generation. If they have a unique idea, they have the necessary stuff for it. I think this could be something which is really making or breaking India's growth trajectory. I think we are all aware of what IIT Madras, IIT Bombay are doing. And I don't consider NITs as laggards, but we can do much more here by providing definitely incubation support. I think ATAL startups team is really a game changer in that aspect. Having personally experiencing or navigating the incubation support for it, I think incubation support is a legitimate good way to go on about partnering with industry. Lastly, I do also want to mention AI ethics. Not short time ago in Paris, Mr. Modi, our respected prime minister, stated this important thing. AI often fails to generate an image of a person writing with their left hand, not the right hand. What might be the case that this is happening? This is specifically after even you prompt the ChatGPT or your respective AI model to generate the right hand image, but it does not. The problem here is that we are talking about the bias. A little bit more time ago, there was a problem with Gemini, the Google's AI model. It was generating a black person if prompted to generate an image of the founding fathers for USA. So the inference here is that whatever data the AI models is being trained on, it imparts a selected bias to those models. And again, the adage here is trash in, trash out. So it is important for us to be bias free when providing or training the AI models, as it could result in a lot of potential harms. So bias and fairness is one bit where we are training the data from one plant type only. We are over optimizing it for profit versus safety, applying it for hydrogen. This is really, really important because there is nuance and not everything is how it looks on paper. Discriminating against certain operating conditions. There is definitely safety risk as well. The model drift in one particular setting might result to incorrect predictions, which might really, really hamper both profit and the safety. There could be cyber attacks on the sensors. We also are over relying on models which might reduce human vigilance. There is economic aspect of it, the job displacement for operators, concentration of powers for the big industrial people, and IP concerns over the model ownership. And there are environmental factors of it. The policy in India, as I'm aware of, is that Niti Aayog principles mandate AI systems to be transparent and explainable, with explanations accessible in multiple Indian languages as per 8th schedule requirements. This is a good way on to go on about it, because India is a very diverse land with multiple languages, and we should be mandating AI systems to be transparent and explainable. However, AI is a black box. We still don't know how the neurons function and what they do. There is a field on for it. It's called mechanistic interpretation, wherein the researchers are trying to prompt it and understand the internal workings of the neural network, or LLM in this case. But it's really, really important to figure out fact from fiction. We can be mandating different things, but if the underlying architecture is not really, really not really, really working and applicable to the particular architecture of the model, then all these enforcement or the rule making might be non-essential. Okay, what can we do about it? The mitigation strategies for technical and organizational are as follows. We can have a diverse training set. We can look through different sites of training data, possibly gathering access to it. In an industrial case, it doesn't really, really make good sense, because the data for your facility might not be shared with a different facility. So there is a bottleneck about it. But the good thing to go on about it is actually having a diverse training set, continuous model monitoring, model versioning and rollback. If you think the new model update is not good, then perhaps we should be actually rolling back. From an organizational point of view, we should actually be having an ethics review board. What is ethical, what is non-ethical from the perspective of hydrogen plant is imperative. Transparency reports, operator training programs, explainability requirements, and clear accountability. From a regulatory point of view, we should be developing AI certification standards. Analogy for this is, if you cannot trust an output, I think it was India who mandated it, but I'm not really sure about this particular fact, that everything that has been generated by an AI model should be labeled as AI. That's a good way to go on about it. But I'm pretty sure, even for all the people who are doing the AI fact check or AI text check, if you put in the preamble of India, the Constitution of United States, it still would display that it's AI generated text, which is hilarious. But I also want to mention this, that yeah, these AI fact checkers or textual checkers don't really, really work. So it is important for us to work on these following aspects, such as AI certification standards, accountability aspects, audit trail, liability frameworks, and a right to human review. The human should be present at least for as long as we can do it. And some of the best practices are that we should be employing them, discussing all the stakeholders involved, doing a risk assessment through the design phase, doing an ethical impact assessment. In the development phase, we can have a diverse data collection, bias testing, explainability built in, and security hardening. For the deployment phase, we can have a full phase rollout, doing it in chunks rather than straight up from 0 to 100%. We can have shadow mode, where AI recommends, human decides. This is how you're doing feedback to the AI models as of now as well. Performance monitoring and feedback loops. You can also have an operational phase where you do continuous validation step by step, again in chunking. Incident reporting, model updates, and human override should be always visible and available. The golden rule is that AI should augment human decision making, not replace it, especially in safety critical hydrogen systems, at least for the next few foreseeable years. Okay, I am going to rush through it because we are out of time and I don't want to take up the time for the next selector. But this is here we are now. On the top side, you have the years 2020 to all the way to 2035. First wave comprises of the basic IoT automation, the digital twin, the blockchain certification. Wave two comprises of fleet digital twins, federated learning, quantum enhanced AI perhaps. And wave three is basically all autonomous. You have color coding here as well. Wave one represents all the things that have been completed or are being worked upon and deployed and commercialized. Wave two is what is being under deployment, is not really active as of now. And wave three is planned. And this is something that India can capitalize upon, such as self-optimizing systems, AI design catalysts, and fully autonomous plants. Federated learning, what is it all about? Again, this basically says that if you have three plants working on their own, then perhaps you can have a big AI model which can learn from all the workings of these plants. And this could be done in a pilot manner, in a pilot deployment fashion, wherein an example would be that we pitch this to Tata Steel on how their direct reduction of iron ore is working with the help of hydrogen and AI systems across all their Indian facilities of steel making. And we could learn the nitty-gritty stuff, such as the operational runtime, what is the electrolyzer efficiency, how is it reacting to the input electricity requirements, what is the major yield, what is the capacity factor to it, when should we tone down the production rate. And all of this is implemented in the global model, wherein once you do this federated learning, you can actually deploy it all across other models too. So what it does is it improves your learning. It is faster. It increases the training data for the AI models and actually is increasing the efficiency as well. Now, for an autonomous hydrogen technology stack, we have the four different levels of autonomy. Level 0 is manual, assisted, partial, conditional, highly autonomous, and full autonomous. They are respectively targeted with years of when they would be deployed. But on the left-hand side, you have the lowest of autonomy. On the right-hand side, you have full auto. And this is how the data flows from the sensing layer to edge layer to the control layer and to the cloud AI, with having digital twins and human oversight. And I think humans should always be part of the equation, at least for the foreseeable future. There is a pilot of this particular facility, which is Air Liquid's 20 megawatt Trailblazer plant in with Siemens Energy in Oberhausen, Germany. And the current status is that human operators are going through 24/7 shifts with 10 to 50 manual interventions per day. Response time is minutes to hours, which could be cut down. Next up, we have a green hydrogen digital trading platform architecture. So we can do a trading wherein the producers and the off-takers are integrating or interacting in this trading platform. The trading platform also goes through the guarantee of origin or the GHCI certificates via blockchain and is being fed into the IoT data feed. The key platform features for a potential of this case would be that it offers green hydrogen European certification, offers real-time pricing, smart contracts, and a QR verification. There are some operational platforms such as High Exchange in Netherlands and Japanese H2 Exchange, which are working with this. For India, perhaps we could leverage an NGHM, National Green Hydrogen Mission backed exchange. But this could be really helpful because we are actually having the least amount of cost for producing green molecules. There's also this one more trend, which is hydrogen as a service. Herein, the project developer traditionally, and you have the provider. Project developer buys an electrolyzer, operates it, maintains it, bears all the risk. It's highly capex intensive, but for traditional, the provider acts as an EPC, constructs and commissions. In the new case for Haas, hydrogen as a service, the project developer or the person actually just pays for every kilogram that he's consuming. And the provider actually owns and operates the plant and guarantees the output, bears the operational risk, and offers digital monitoring too. So some of the key players in this are Hydro Energy, Protheum, Hygenco, not necessarily, but there is Life. Something specific that I also want to mention, because we have been talking about this Oaco, and these are the last two slides that I have to offer. So I think I'm going to be wrapping it up. But the project was basically about coupling all the different sectors. So Oaco steel facility operates on using this scrap steel. It uses power grid electricity, uses water for electrolyzer, power for electrolyzer, produces oxygen and hydrogen, also uses LPG when electricity prices are too high to support electrolysis. So they use LPG as a substitute heating. The heat from electrolyzer is used as a district heating because it's housed in Sweden, and especially during the months of winter and autumn, there could be a good benefit. The hydrogen, when not used for oxy fuel for generating or rolling steel, could be transported to heavy trucks, and it's also producing steel products. So now imagine like this is what the sector coupling would look like. And this equation actually targets the chicken and the egg as well. And this is the pilot project itself, but they have deployed about 20 megawatts of electrolyzer system in Oaco Hofosh. And what I did in necessarily was I was determining the optimal times for storage of hydrogen, when to produce by doing the advanced data analysis on the time series for future in respect to the electricity prices, and developing a model between electricity prices to hydrogen storage in our shell. And this is me wrapping things off, but we have resources and further learning, journals to follow, open source tools, and a personal recommendation for what Chhattisgarh's hydrogen future would look like. So I know that we have a recent AI data center park in Nava Raipur, which is being inaugurated. Chhattisgarh is also having a rich industrial base, such as mining and steel companies. So DRI-based steel production using electric arc furnaces could be deployed there. They could also be deploying hydrogen powered trucks and automated technologies to lower the carbon footprint and boost sustainability. In essence, we learned all about the following four things, and that's me wrapping things off.
Yeah, thank you, Mr. Akam. Um, uh, Participants, do you have any questions? Please feel to ask. Maybe one or two questions. Hello.
Yeah, hello. Yeah, yeah, Professor Sami, if you could allow me, if I'm able to speak something.
Yes, yes. Yeah, please proceed, sir.
Yeah, thank you so much, Professor Sami. Yeah, Professor Sharma is a wonderful presentation. Maybe sorry to say that because I came in between that. It was really the presentation is very excited on AI and ML on this hydrogen storage and other things. See, can you give some kind of throw the lights on how we can get some kind of linkage to the industry angle for getting the maybe tie up with that hydrogen storage the project, or we can say that kind of research we want to do in that particular areas.
Mm, I am not really aware of the industrial aspect of what industry wants in India. I want to mention this because I had recently moved from Sweden to India about 8 months ago, and this was on the premise of me starting my own startup. So I don't really know what is the industrial landscape in terms of uh, Indian industrial people or stakeholders wanting in terms of hydrogen storage or AIML. But a general rule of thumb would be that to run electrolyzer performance optimization, or perhaps long short term modeling, deploying neural networks to model what future of electricity price as to storage could be, because this is again like something which is really important. And I think this would be deployed into factories across Chhattisgarh or wherever there is a DRI, a direct reduction of iron ore, is being taken place. Because I think Odisha is also incentivizing by having direct hydrogen policy. It's unfortunate because Chhattisgarh is landlocked and doesn't have water access, which is the case for Rajasthan, where I'm coming from as well. But we do have large industrial base and we do have solar. So there is direct end-to-end integration opportunities for industrial collaboration. But to answer your question directly, I am not particularly
Yeah,
aware of
yeah,
it.
Professor Sharma, I think it is a fantastic answer. I got your answer. See, of course, we all working on this hydrogen storage, and of course, there is a pipeline corrosion also. The biggest issue which we are looking for future, that there should be a like a hydrogen development, and maybe if the industry people, because this sort of project, this sort of research problems, normally the agency are trying to get it some more exposure on other angle rather
Hmm.
than the lab scale project. Okay,
Yeah,
so sometime lab scale project is something that which cannot be handle the hydrogen as well as the pipeline, online pipeline system
yeah,
which
the
can.
blending.
Exactly. So I think it's fantastic PPT and as well as your answer. Thank you so much, Anna.
Hmm.
Thank you so much,
Uh,
and thanks
to
to the organizer also. Yeah,
to
please.
answer directly, I mean, my particular case where we were modeling this, we were evaluating whether to lay down a pipeline from the facility to the refueling station or to actually deploy trucks for refueling. And the problem in that case was that the distance between the facility to the refueling station was less than a kilometer, but we were still collaborating whether to actually deploy a hydrogen pipeline, because the hydrogen pipeline for 100% hydrogen to be transported from the facility to the refueling station is absolutely ridiculous in terms of cost. So, but on the cost frontier, it was actually cheaper for us to deploy the hydrogen trucks. So I do get you. And then there's the question of the hydrogen embrittlement, because
Yeah.
the natural gas pipelines, India is experiencing about 10 or maybe 20% blending. But yeah, it will take time. But it's good to research on these frontiers, the techno-economic analysis of whether a pipeline is good, or perhaps we can alternate a different future or like a different way. So thank you, Professor Suresh.
Yeah, thanks to Anna. Yeah, I'm just to the organizer, please.
Yeah, thank you, sir, Professor Suresh, sir.
Yeah, thank you, man. Professor Swami. So I heard about few things on you. You are doing wonderful work. I just had a time, so I want to listen a few things from Sharma, and it's a wonderful. Maybe of course, Saturday I have one presentation, of course, related to the hybrid hydrogen system. So
Yes,
anyway,
sir.
yeah, please carry on, please.
Yeah, yeah. Thank you, sir. So, any more questions? Already we are delayed some 20 minutes. So we'll proceed to the next section. Before going to the proceed to the next session, I want to give that we extend our sincere gratitude to the our speaker, Mr. Akash Sharma, for delivering an insightful and engaging expert talk on digitization in the AI in hydrogen systems. Sir, your presentation provided a valuable perspectives on how digital tools, data-driven optimization, and artificial intelligence are transforming hydrogen production, storage, distribution, and safety monitoring, how to build the first AI model, industry collaborations, and AI ethics and responsible deployment, many more you shared. And the practical examples and forward looking insights you were shared have greatly enriched the understanding of our participants and enhanced the quality of our session. We deeply appreciate the time and effort and expertise you contributed to this program. Your talk has inspired meaningful discussions and opened new avenues for research and industry collaborations in the hydrogen domains. Thank you once again, sir, for your valuable contribution and for being a part of our academic initiatives. Thank you very much, sir.
Thank you, Professor Swami, and thank you, Professor Bhargavi, for giving me this opportunity. I'm absolutely sorry that I've overtaken the next speaker slot as well, but thank you so much.
Yeah, thank you, sir. Have a good day, sir. We'll
Yeah,
see you
thank you,
again, sir.
Mr. Ekansh.